So much for this introduction. Thank you all for sticking for the last presentation. I'll try to, I know we're running out of time a bit, so I'll try to stay in time. Today I'm going to be presenting a project that we have developed for the synthesis of N-substituted 3-amino-2 pyridones. Just before, I don't see, you guys see my screen, everything is working right now?
Yeah.
Okay, yeah. Awesome. I'm just going to take the pointer out. So this project stemmed from a medicinal chemistry effort that we were pursuing here at Biogen, in which we encountered this motif, these moieties that we saw a need to innovate in order to synthesize faster and accelerate our SAR development for the medicinal chemistry efforts. And so at large, pyridone have been found to be useful for a number of different applications. And here what I'm showing is this orglet that was published in 2018, used them to promote directed CH bond activation. On the right here, you have some examples of non-directed CH bond functionalization of arene, where the pyridone was utilized as a ligand for the palladium. More closely related to what we do in pharmaceuticals, I would like to bring your attention down to this table where you have a number of different drugs that were synthesized and developed containing two pyridones. Now, these are not necessarily synthesizable through the method that we have developed, but these are nonetheless a number of successful examples where the pyridone motif have been introduced in life-saving molecules. And so I think that I wanted to give an appreciation on how often this has actually been found as a often a phenyl bioisoster in drug discovery. In fact, I think that you get a better appreciation of its potential for being a bioisoster for phenyl when you looked at simply the lipophilicity of these compounds. So this is a table that was generated, the values from calculated from the ACD lab software. I think you can use about any chemistry software to calculate C-log-P these days. So just as a reference here, you can take phenyl, which is labeled 14A, which has a C-log-P of 2.2. Going down the road of adding heteroatoms such as this phenol, the pyridine, or this N-oxide pyridine, you will find that the C-log-P will decrease as expected, up to down to negative 1.2 value for the N-oxide, which at first glance, before calculating anything, I would have thought this was probably the most polar analog here in the table. But when you look at the value for 14E, which is negative 1.3, you realize that these motifs are the two pyridones are extremely polar, in fact, without bearing any charge, which is really interesting for medicinal chemistry purposes. And so I think it's well accepted that as medicinal chemistry project grows from hit to candidate selection, you tend to increase the size of those molecules significantly, and it tends to go on the side of the more lipophilic or higher lipophilicity. And I think here I've extracted an example from AstraZeneca that shows exactly that, where they have this lead candidate that described as 16A, which had great potency, but unforgivable solubility profile, which I think is detrimental for a number of reasons beyond formulation. I think that solubility oftentimes comes as a problem when it's that low in terms of reliability of the data readout for the assays, for primary and secondary assays that you're going to look at. And so in this case, what they did is what I think most medicinal chemists would do, is go down the bioisoster route and try different cycles. And they found that 16D here, which is bearing this 2-pyridone motif, retained the interesting potency, and then lowered the C-log-P predictively, which they found increased the solubility to something that they could manage. Other applications for our properties from the pyridone is their potential for hydrogen bond donor acceptor, which in this case, this Merck paper described as replacing this pyrazolo-cetamide motif in order to maintain the hinge binding region, which improved their potency, and then the LLE value went up by almost 1 unit. And lastly here, I would like to bring your attention to the bottom right of the screen, where you have these preclinical lead molecules bearing the 2-amino pyridone motif that we are talking about today. So this here is extracted from our patents, and it was the reason why we went down this road, where we're bearing all these 2-amino pyridones with different alkylation products here. So initially, in order to service our SAR, we started with what we call the oxopyran to pyridone route. There's a number of ways that you can make these motifs that existed before we came in this work, but a lot of those are lengthy and just, you know, it's high cost in labor to produce all the analogs. And when we're going down the road of, you know, analyzing a lot of different molecules, and these are building blocks we're making, right? So in average, we would take a week to make one of those. So we were looking at different strategies to enable those building blocks. And so we looked at some CN couplings that we found in literature, as well as Chan-Lam couplings. And the oxopyran route was what we've used the most initially. These are, this is a building block that was commercially available. It was a little more expensive than what we wanted to for something like this, but it served the purpose. 4 steps down the road, purification, we would obtain the building block in about 17% yield, which was fine because it was the last step of our total synthesis for this, the analogs we were making, but still, as I said, laborsome. So we found in this, I think it was a BMS patent, embedded in there was this coupling, the CN coupling listed here, where they were describing making some of these building blocks in quite low yield, but the direct approach was appealing to us, and we thought maybe we could optimize it. So we were able to reproduce the reaction, but what we found is that it was not very amenable to modification on the substrate scope. And then when we started to go to rings that were more interesting for us, such as the cyclopropyl, we found that it was not translating. So we saw this paper in SCS MedChem from 2019 that was describing this Chan-Lam coupling, which was actually, we were able to reproduce it as well in our labs. And we were very excited about this. And so we decided to go down the road of an optimization campaign for this reaction specifically, in which we eventually went for the BF3 salt as a better coupling partner. And I'm not going to talk about all the different conditions here. I'll just point out to line 7 in light of time, that this is what ended up being the better conditions to obtain this product. And so this was a really good optimization campaign where we were able to isolate in average about 68% yield of this building block. So unfortunately, again, just as the CN coupling, when we tried to modify ever slightly the nature of the substrate for this reaction, we found that the reaction was very sensitive to these changes, both sterically and electronically. And so we found that we needed to go through a more general methodology that would, hopefully enable parallel medicinal chemistry. So in parallel to this, we were investigating, the oxopyran route. We found that you could go through this diene addition instead, adding your amine to this. With some heat would add properly, and then upon heating overnight at 130 would cyclize to the desired pyridone with an bearing an ester. Saponification and aqueous rearrangement further, we would obtain this protected bocamine that we would deprotect to obtain the desired product. This was extremely reliable. This product is commercially available. Well, we decided to make it ourselves because of the ease of synthesis, really, this was something that we did for a good while, and was, I think, found in a number of patents as well. I think I found it's probably an AstraZeneca patent that used 100 times this synthesis for different building blocks. But it's 6 steps, yields about 22% for purification, and each analog takes about a week to complete. Our scale-up group was not too pleased either to work with aqueous rearrangement. I mean, we say 2 grams here. They are able to scale it up, but they prefer not. It's a reaction that creates a lot of waste as well. So that's what we aim to remove initially. By going to this nitro ester building block instead of the this ester up here, we hypothesized that it could potentially engage in a Novanagal condensation in the same manner as above to create this intermediate. This intermediate we expected to be higher in energy, so we were not sure if it was going to be able to perform the sequence to provide the desired product. So when we try the reaction with the same acidic conditions to activate the Novanagal condensation, we found that in fact it was possible to make it. It was in fact unstable as well, but if handled properly, this increased level of energy on the material could also be used to our benefit, where upon formation, we could just cool down the diene to room temperature and add an amine, which would add in a matter of seconds. What we then found also is that the cyclization did not require 130 degrees Celsius anymore. This would in fact happen if you leave this in the fridge overnight. It would spontaneously cyclize on itself. So this was interesting because then we had removed the Cursus rearrangement as we had strategized, but the benefit added to this was that the whole sequence was now accelerated drastically. This was somewhat unstable. You can flash the intermediate, but it does degrade on silica, which you can assess by 2D TLC. And once purified by silica, you would obtain it in about 70% purity, and you can keep that in the fridge for a couple of weeks and then reuse it. So it is going to degrade on the bench over the course of a day, but I think that if kept cold, it's something that you can actually handle, with reasonable ease. So in this case, what we tried to do also is to match the solvent that was required for the addition through solvent screens with the potential reduction of the nitro in the end, because we had in mind to do a one-pot process. And so here is, I'm showing how we optimize this method. And the first step is the most crucial one, to make sure that you obtain the highest purity, highest yield of the diene intermediate. This table shows the starting material, the tetramethoxypropane to the nitropyridone, because as I've stated before, the intermediates in between those two will tend to be somewhat unstable, and even after the amine adds to the diene, tend to cyclize to the pyridone. And so ever so slowly, just for I think having a solid reproducible yield, quantifiable, we would prefer to have the nitropyridone as an end product. Also, I think that just solidifies the methodology as reliable. So we evolved this with a screen of acid, with being conscious about the different pKa's that we were screening for to try to see where this would initiate. And we found that oxalic acid was about where the threshold lied. If I have to propose, just based on experience, an acid that I find just easier to handle is the TFA in this case, because it's more forgivable than sulfuric acid. And I think on a small scale, 1 gram more or less, at least for our purpose, we would use TFA despite the slightly lower yield and a little bit of, I don't want to update my, I'm sorry. The slightly lower yield of TFA, I think, is acceptable in terms of just the ease of handling. So sulfuric acid is more efficient. We did not use 1% just to show that we could be more efficient, but using 10% of sulfuric acid would start to degrade the intermediate. So that becomes handy, though, when you scale it up. So here I'm showing that in lab, I used the sulfuric acid to do a 10 gram scale of this reaction successfully with the same yields as before. But you have to bear in mind that, at 1 gram scale of this tetramethoxypropane, you're talking about less than 5 microliters of sulfuric acid. So it's hard to, gauge properly. The second step was that we optimized was then the reduction of the nitro. And so we looked at an array of different reduction reaction conditions, and we found that iron, ammonium chloride in methanol water with the gentle heat would provide quantitative yields. And then same thing goes for transfer hydrogenation as well as traditional hydrogenation with hydrogen gas. All three could be used. I see scenarios where people would prefer to use one over the other for a multitude of reasons. So we wanted to give just a different array of possibilities to enable this as a one-stop shop type of reactions to and process to the people to enable these synthesis. So that brings me to the scope of the reaction. And here you can find that, we had the cyclopropyls that we were looking for, as well as some quaternary centers that we were interested in looking at. But also we try to expand it to other rings that, of course, you can, make a graft on to a pyridone through different means. Probably some are easier than this method or more direct, but still, I think we wanted to just show that this was possible, such as methylamine, and as well as some aryls. So the heterocyclic amines needs to be, electron neutral or electron rich trending amines in order to cyclize properly. Electron poor arenes are going to be adding on the diene, but they have a really hard time cyclizing. I will mention also that there's the choice of solvent for methanol over, say, ethanol, which is more environmentally friendly, is conscious because we've seen a significant amount of acceleration in the reaction rates for cyclization with methanol over ethanol at the same temperature. So, for example, this amine P would cyclize in ethanol over about 5 days, where in methanol will take about 48 hours. Additionally, we tried to introduce some more sensitive groups. So, for example, here, chloride, bromide on an alkyl, an olefin and alkyne. These we decided to show them by stopping at the nitro level, because we figured that the experimentalists that would go through this, adding those building blocks to the molecules, would probably want to derivatize them further before unmasking the amine anyways. And also, I think for reasons of, compatibility with the reduction stage subsequently, it was preferable to stop here. And finally, we did try to introduce some substitutions on the core of the pyridone by condensating with some of these ketones. As described, the method was not amenable for these changes. And so, unfortunately, we were not able to produce those. But I think that by modifying the, that's in the hypothetic world, but I think that it is possible to do the condensation on these with different conditions, but we wanted to make sure that the conditions were, as streamlined as possible. So I think that, as described, this is not possible. So in summary, we were able to do a truly one-pot process over 4 steps that required only 1 purification in the end. And we improved the yields versus the previous syntheses that were available. And I think it's one thing that I would like to impress also is how little waste is produced from this reaction. The first step is neat. And then we introduce 1 solvent that is carried through all the way to the end, including the reduction step. So we reduce the amount of waste far beyond removing the simple Curtius rearrangement. And this has a very large impact, as well as reducing the time to synthesize these, which used to take a week, and now we're enabling them in 1 workday. So with this, I'd like to thank you all, thank the organizing committee and my team here at Biogen, Magnus, Emily, Vanna, and Steve. And I'd like to also acknowledge Professor McMillan that has been consulting for us on the medicinal chemistry project and gave his opinion on this as well. If you have questions.
Thank you, Philippe.